Tonight, anticipation fills the solar system. 3/Atlas, the third interstellar object ever discovered, is about to make a close pass by Mars, coming within just 0.19 astronomical units. Every Martian orbiter is focused on gathering as much information as possible during this rare moment, yet this encounter stands apart from anything seen before. Its intense green glow, unusual shifts in velocity, and the presence of carbon dioxide have already left scientists puzzled. Soon, telescopes on Earth will no longer be able to track it, and only a few orbiters circling Mars will continue watching. The mystery remains, is 3/Atlas merely an unusually strange comet, or could it be something artificial, something that challenges what we believe about intelligent life beyond our solar system? As it draws nearer, researchers are hoping that signs such as fragments breaking away, unexpected signals, or curious patterns of light will offer deeper insight into this enigmatic visitor from another star. The coming hours may reveal something extraordinary, or confirm that science can still explain the unknown. With only 6 hours left before the sun hides it from our instruments, 3/Atlas will sweep past Mars at a distance of 0.19 astronomical units, about 28 million kilometers, racing through space as Earth's watchful gaze begins to fade. The upcoming communication blackout isn't caused by any malfunction or poor planning, but simply by the natural positions of the planets. During this short window, Mars becomes the ideal location for observing events across the solar system. All major spacecraft orbiting the planet, including MAVEN, Mars Express, and ExoMars TGO, switch to intense observation modes, carrying out pre-planned procedures while staying ready to adapt quickly as new situations arise. Inside the MAVEN mission control room, the Red Watch team takes command. These highly trained specialists are responsible for managing emergencies and making critical decisions if anything unexpected occurs. In the days leading up to the blackout, they rehearse switching rapidly between regular scientific operations and rapid response data collection, preparing to act immediately if a sudden burst of energy appears or a potential debris alert is issued. Backup systems are activated, thorough checks are conducted with the Mars Express and TGO teams, and every command is carefully documented. All data is duplicated to prevent any loss. With the rest of the solar system unable to observe events directly, there can be no vulnerabilities. The observation plan is tightly structured. Mars Express will capture wide-angle images at frequent intervals, which will later be combined to detect even the smallest fragments breaking away or any unexpected changes in the object's path. TGO's instruments sweep through the Martian atmosphere, searching for any unusual light signatures, while MAVEN's sensors focus on detecting disruptions in the upper layers that might point to something unexpected. Both spacecraft are pushed to their limits, using every ounce of power and every available second of communication time according to carefully synchronized plans. If a threat from orbital debris arises, Mars Express is programmed to switch into a safe mode, prioritizing the spacecraft's survival over continued scientific observation, and the threshold for declaring an emergency is set only slightly above the latest rise in particle density, meaning even small changes are taken seriously. The communication blackout between Earth and Mars is more than just a pause in contact. It serves as a real-world test of the capabilities and reliability of all instruments on the Martian side. The Red Watch Coalition functions as the mission's decision-making center, issuing commands and updates during the brief windows when communication is possible, ensuring every system remains operational and coordinating efforts with surface rovers like Perseverance and Zhurong. In mission control, the countdown continues as the comet draws nearer. Beyond the official teams, networks of amateur astronomers around the world are on alert, ready to report any sudden spikes in brightness to the global warning system. Over the next 6 hours, the outcome, whether 3/Atlas proves to be an unusual natural object or something artificial, will rest entirely on the performance of a handful of orbiters and their crews. The pressure is immense, and the margin for error is almost non-existent. With each passing second, the stakes grow higher. Since 3/Atlas was first detected, peculiar signals have been recorded. The earliest hint came from a backyard telescope in Pune, India, where amateur astronomer Priya Ralo noticed a repeating pulse in the light, a rhythmic brightening and dimming unlike anything described in comet studies. Her observation quickly drew widespread attention, and the mystery deepened once professional observatories began tracking the object. Detailed light measurements revealed that its brightness rose and fell at remarkably consistent intervals, a pattern far too regular to be explained by random gas emissions. Each pulse of light appeared abruptly and then faded smoothly, almost as if it were being deliberately switched on and off. Even as the object moved closer to the sun, this precise rhythm remained unchanged, unaffected by variations in distance or solar radiation. Further analysis of the light brought another unexpected finding. Instead of the usual dominance of water vapor in a comet's emissions, carbon dioxide turned out to be the main component. Its abundance was striking, more than 8 times higher than water, far beyond what is typically observed in comets that release volatile materials. Scientists attempting to replicate this composition in laboratory conditions have struggled to match what the data shows. Adding to the intrigue, the cloud surrounding the object glows an intense green, peaking strongly at 516 nanometers. This distinctive color has been consistently recorded by instruments both on Earth and aboard spacecraft. Conventional explanations, such as emissions from C2 swan bands or carbon monoxide, fail to account for the brightness or stability of the color. Another anomaly appears in the spectral data. Nickel emissions are at least 4 times stronger than those from iron, the reverse of the usual ratio seen in comets. High-resolution images and polarization measurements further complicate the picture, revealing details that challenge current scientific understanding. The bright green glow coming from the coma shows a strong negative polarization, a property typically observed in certain asteroids rather than in icy comets. The dust tails also behave strangely, consisting of larger, slower-moving particles whose paths are far more difficult to predict. These particles don't scatter quickly like normal comet dust, but instead spread gradually in a broad arc, as though they're being released steadily over time rather than ejected in sudden bursts. Tracking the object's motion reveals subtle shifts in its speed that don't align with any known pattern of gas escape. Each of these changes coincides with a pulse of light, suggesting a direct connection between the illumination and the acceleration. None of these anomalies alone would be enough to raise suspicion, but taken together they form a picture that doesn't match any recognized category of cometary behavior. All types of observations, from light curves and spectral color analysis to trajectory data, contribute to a growing list of unexplained features. The evidence is there, waiting for a single explanation that can tie everything together. Scientists have approached the problem using fundamental principles of physics and chemistry, and 4 main theories based on existing knowledge have been proposed to explain the object's peculiar nature. One leading idea suggests that the object's unusual composition formed under extremely cold conditions. According to this hypothesis, 3 Atlas may have originated far from any star, in a region where water remained frozen solid, while substances like carbon dioxide, carbon monoxide, and other rare ices accumulated in abundance. Some comets believed to come from the Oort cloud support this type of environment. However, none have ever shown such an extreme carbon dioxide to water ratio, exceeding 8:1. Even so, proponents of this idea argue that interstellar space is vast, and our sample size of known comets is small, meaning that a single unique example could expand our understanding of cometary chemistry. Another explanation looks at the comet's internal structure. It's possible that pockets of trapped gas beneath the surface are bursting open as sunlight penetrates deeper layers. If these pockets are unevenly distributed, they could account for the consistent changes in brightness. Laboratory tests support this idea, showing that even small temperature variations can trigger sudden jets of material, and if the layers are arranged in a particular way, these outbursts can repeat in a regular pattern. Although this type of predictable activity is uncommon, it's still plausible for an object that has been shaped over billions of years by the harsh conditions of space. A third theory centers on dust dynamics. The comet's bright green halo and the presence of large, slow-moving particles might be explained by unusual dust composition or how those particles are arranged. The solar wind and Mars' weak magnetic field could also be shaping the tail, organizing charged particles into broad, curved structures. Research into comet tail shows that heavier particles often drift behind in specific formations, moving slowly in sweeping arcs that resemble the bursts now being observed. The negative polarization, more typical of asteroids, could indicate that the particles are dense and carbon-rich rather than light and icy. Another possibility is that our current scientific models simply fall short. With only 2 other interstellar objects studied before, each new discovery pushes the limits of our understanding. Subtle changes in velocity and recurring outbursts might reflect physical processes our simulations don't yet include, such as complex interactions between sunlight, gas release, and rotation. From this point of view, the strange behaviors may not signal anything artificial at all. They might instead highlight how much we still have to learn about these rare visitors from beyond our solar system. For every unexplained observation, scientists aim to exhaust all conventional explanations before considering more extraordinary ones. During the crucial 6-hour window, Mars becomes the only location capable of collecting meaningful data. 3 spacecraft, MAVEN, Mars Express, and the ExoMars Trace Gas Orbiter, take the lead in gathering nearly all the information about Comet Atlas as it approaches. Each of these spacecraft is equipped with specialized instruments designed to detect specific signs of activity. MAVEN's ultraviolet camera monitors the faint glow from the comet's tail, searching for sudden flares or any signs of fragmentation. Its particle detectors and magnetic field sensors operate continuously, watching for sudden increases in particle activity or unexpected changes in Mars's upper atmosphere, possible indicators of unusual interactions. If the comet's dust or energy interacts with the planet's air, MAVEN will likely detect it first. Mars Express contributes by capturing detailed images with its cameras, using long exposures to trace changes in the comet's bright region and watching for structural shifts or breakups. Its spectrometer analyzes the light spectrum for any unusual patterns, unexpected emissions, or signs of missing water. The Aspera 3 instrument focuses on detecting energetic particles, which could signal complex interactions between the comet and Mars's environment. Meanwhile, the NOMAD and ACS instruments on the ExoMars TGO search the comet's thin atmosphere for rare gases, atoms and molecules that don't normally occur within our solar system. The KSSIS camera works to capture images of the comet shedding material or releasing clouds of dust, providing visual evidence of any dramatic changes during its close pass. All the information collected by these instruments is carefully time-stamped and shared immediately among the various scientific teams. On the Martian surface, the Perseverance and Zhurong rovers joined the effort, searching for signs such as unusual dust deposits, shifts in atmospheric composition, or unexpected lights in the sky. While their sensors and cameras can offer valuable supporting evidence, they lack the sensitivity and precision of the instruments aboard the orbiters. The observation checklist is detailed and strict. Scientists look for fragmentation patterns, trajectory changes following bright flares, spectral or radiation signatures that defy known explanations, isotopic ratios beyond typical solar values, and any signs of engineered timing in pulses or movements. No single piece of data is considered conclusive on its own. Every anomaly detected by one instrument must be verified by another before it can be taken seriously. Only when multiple lines of evidence converge from different instruments and vantage points can an observation move from merely unusual to truly extraordinary. Every data stream from Mars undergoes rigorous scrutiny before it becomes part of the official scientific record. The first safeguard is redundancy. Each packet transmitted from orbit is copied, time-stamped, and archived by independent ground stations on both sides of the Atlantic. This system protects against solar interference, transmission errors, and the rare possibility of data corruption during the blackout period. Telemetry delays, sometimes lasting hours as signals travel through relay satellites and deep space antennas, add another challenge. To address this, mission teams prioritize packets marked as anomalous, such as those indicating potential fragmentation, unusual spectra, or sudden shifts in the comet's path, and run them through rapid cross-checking protocols to confirm their authenticity. No single sensor or research team can confirm an alert on its own. Every potential event must be independently verified by at least 2 different instruments, and once bandwidth allows, the unprocessed data is uploaded to open archives for anyone to review. The strict chain of custody extends beyond just numerical data. If an orbiter's collector captures a dust particle or ice fragment, planetary protection specialists immediately take over. These experts enforce rigorous handling procedures. Samples are sealed, barcoded, and recorded with digital hashes that require joint approval from both NASA and JAXA before any analysis begins. The aim is to guarantee complete traceability. Any organic signature detected in Martian soil or the atmosphere after the flyby must be clearly linked to its source. Future missions searching for signs of life rely on distinguishing what material originated from 3/Atlas and what is native to Mars. Even metadata, including time, location, and instrument calibration details, are stored in tamper-proof logs, ensuring that every unusual result can be audited far into the future. Beyond the mission control centers, a network of citizen scientists springs into action. Amateur astronomers from backyard setups in Pune to automated observatories in Arizona transmit brightness and position data to shared shared online databases. The first sign of a sudden light variation might come from an individual observer, but specialized teams quickly review these submissions. Official statements from scientific organizations, encouraging caution and context, are only issued once multiple instruments have confirmed the observation. Extraordinary claims demand equally strong evidence. Communication plans for every possible scenario are designed to deliver clear, accurate information without unnecessary sensationalism. The entire process is open and transparent, built around layers of verification, redundancy, and careful documentation. Every step is intended to inspire trust and ensure that any final conclusion is supported by evidence that withstands scrutiny. Inside the RedWatch Control Center, a clear decision framework shapes every discussion. There are three possible outcomes for the analysis of 3/Atlas: safe, risky, and extraordinary, as data streams in from Mars. The safe conclusion is reached if all unusual readings can still be explained by natural comet behavior, repeated gas jets, dust particles with odd but natural chemical compositions, and slight velocity changes that remain within the boundaries of known physics. The situation becomes risky if fragments or debris clouds exceed critical thresholds, if the object loses more than 10% of its total mass, or if there are sudden course changes that could endanger Mars orbiting spacecraft. In such a scenario, protecting instruments and organizing data quickly take priority over continuing scientific measurements. The extraordinary classification is reserved for a very different level of evidence. It requires at least two major independent anomalies, such as synchronized signals occurring alongside small velocity shifts, or light spectra that don't match any known chemical, and these findings must be confirmed by separate teams using different instruments. A single anomaly, no matter how unusual, is not enough. The guiding principle is clear. Only when multiple independent lines of evidence align can the possibility of an artificial origin be considered. Everyone involved understands the stakes. During these decisive moments, the data becomes more than just information. It shapes the next steps in planetary science. Updated protocols now require that all data from a flyby of an interstellar object be made public within hours, rather than months. The era of keeping such discoveries confidential is over. NASA, the European Space Agency, and JAXA have all agreed to maintain mirrored data repositories, ensuring that both raw and processed information are uploaded to public servers as soon as ground stations verify their accuracy. Automatic detection systems now flag any unusual or unexpected data the moment it appears, ensuring that such information is immediately prioritized for expert analysis. Alongside every set of measurements, detailed notes describing the exact conditions and methods used to collect the data are recorded, providing essential context and transparency. This careful documentation allows scientists to retrace the steps of the observation, verify its accuracy, and understand precisely how each value was obtained. It also means that even subtle anomalies, which might otherwise be overlooked, are noticed quickly and treated with the attention they deserve. The updated procedures also emphasize speed and continuity in data sharing. Whenever a sudden change is detected, whether it's a shift in brightness, a variation in trajectory, or a chemical signature that wasn't there before, preliminary information is now transmitted almost immediately. These rapid bursts of data serve as early alerts, allowing teams to react without delay. Soon after, a more comprehensive wave of information follows, delivered as high-resolution images, extensive data sets, and analytical reports. This two-stage communication system ensures that no time is lost in the early moments of discovery, while still guaranteeing that deeper analysis can take place once all the details are available. Crucially, this approach also invites public involvement, turning the monitoring process into a collaborative global effort rather than a closed specialist task. Across the world, networks of dedicated amateur astronomers, from the skies above Pune in India to the remote observatories of Patagonia, now play a significant role in this process. These observers, using telescopes ranging from advanced backyard setups to small observatories, submit measurements of an object's brightness, motion, and position directly into trusted data platforms. There, sophisticated artificial intelligence systems organize and cross-check the incoming information, filtering out errors and highlighting results that warrant closer inspection. This process means that a single observation from a hobbyist telescope can quickly escalate into a full-scale scientific investigation, bridging the gap between citizen science and official research in a way that has never been possible before. In terms of planetary protection and ethical exploration, significant new policies have also been put in place. The Committee on Space Research now mandates that any readings that even hint at the possibility of biological activity must be clearly labeled and documented once a spacecraft encounters the source. Furthermore, a complete record of who handled any dust, samples, or organic materials gathered during missions must be maintained, creating a transparent chain of custody for all collected matter. These measures are not designed solely for the upcoming investigations of 3/Atlas, but are now standard requirements for all missions involving potential interstellar objects. The ultimate goal of these changes is to ensure that every discovery, whether routine or revolutionary, it is approached with openness, scientific rigor, and a unified global standard, providing humanity with a reliable framework for exploring and understanding the unknown. On October 3rd, 2025, the object known as 3/Atlas passed remarkably close to Mars, coming within only 0.19 astronomical units of the planet. This rare encounter immediately drew the full attention of every major mission currently operating around and on Mars. The orbiters MAVEN, Mars Express, and ExoMars Trace Gas Orbiter all redirected their instruments toward the object, coordinating an intensive observation campaign that lasted for more than 40 continuous hours. During this period, they collected an immense volume of data, capturing fine details about the object's behavior and properties. Among the most striking findings were the detection of a distinct green glow, brief but intense bursts of brightness, and an unusual spectrum dominated by carbon dioxide signatures, a combination of features never before recorded from any known comet or interstellar visitor. While many aspects of these observations can be explained through conventional scientific models and natural phenomena, significant mysteries still remain. Chief among them are the small but measurable changes in the object's velocity and the precisely timed energy bursts it released, anomalies that defy easy explanation. The complete dataset, which has now been made publicly available, offers scientists and independent researchers an unprecedented opportunity to analyze the encounter in depth. Yet, fundamental questions continue to linger. Where exactly did these unique signals originate? Are they purely natural in nature, or could they possibly indicate some form of artificial influence, perhaps even linked, however remotely, to human activity? What is clear is that the passage of 3/Atlas has left a profound mark on how we observe and interpret objects from beyond our solar system. It has prompted the scientific community to reconsider existing protocols for interstellar monitoring and has underscored the vital importance of transparency and open data in space science. Whether future analysis ultimately confirms 3/Atlas as a natural body with unusual properties or reveals something far more extraordinary, its close approach to Mars has already reshaped our methods of preparation, our strategies for observation, and the conversations we have about what might exist beyond the familiar boundaries of our cosmic neighborhood.